Hi there. Welcome to this exciting tutorial on vapor pressure, an incredibly important topic in both geography and physics. I'm thrilled to have you here. When it comes to estimating the water vapor content in the air, we have two main methods, humidity and vapor pressure. I've already covered humidity in another tutorial, and you can find the link in the description below. I highly recommend checking it out. But today, we're diving deep into vapor pressure. Before we do that, though, let's take a moment to understand where all pressures come from in the first place. Think about the gas-filled containers we use regularly in our daily lives. Have you ever wondered where the pressure inside these containers comes from? Well, let me explain. Imagine you could zoom in and see what's happening inside a gas-filled container. You'd be amazed to see zillions of gas molecules bouncing off the walls at any given moment. But why is this important? To understand, let's take an imaginary container with just one gas molecule. The red dot represents the molecule. Of course, molecules have their own internal structure and are extremely tiny, but we'll keep it simple for now. This gas molecule moves randomly inside the container, bumping into the walls. Every time it hits the wall, it exerts force. This force per unit area on the container's wall is what we call pressure. Here's the mathematical definition of pressure. Similarly, it is also possible to calculate the pressure exerted by this molecule on other walls of the container. But, in real life, molecules move really fast, and there are a lot of them, so the pressure on all the walls ends up being the same. The force that each gas particle exerts on the container walls depends on its temperature and the number of particles. Temperature, in simple terms, tells us how much energy these molecules have. Now, let's add more gas particles to our container. The total pressure is simply the sum of the pressure from each particle hitting the walls. And if the container has a mixture of gases, the pressure from each type of gas adds up. This pressure from each individual gas in a mixture is called partial pressure. Let's say the red dots represent nitrogen molecules, the green ones are oxygen molecules, and the blue ones are water molecules. The total pressure on the container wall is the sum of the partial pressures from nitrogen, oxygen, and water vapor. The partial pressure due to water vapor is what we call vapor pressure. Vapor pressure reflects the idea that when water evaporates, it adds water vapor to the surrounding air, which in turn increases the pressure. Hence, we call it vapor pressure. To understand vapor pressure even better, let's take a beaker with dry air in it at about 20 degrees Celsius. By dry air, I mean there's no water vapor in the air. The pressure gauge measures the pressure of the air inside. Now, let's put some water into the beaker. If we could zoom in on the water's surface, we'd see that as soon as the water is added, some of its molecules start to evaporate. This is called evaporation, while the opposite process, molecules returning to the water, is called condensation. The upward arrows represent evaporation, and the downward arrows represent condensation. Since the air above the water is dry, evaporation will outpace condensation. As more water molecules enter the air becomes moist. The vapor pressure from these evaporated molecules increases the total air pressure, as you can see on the gauge. The change in pressure directly relates to how much water vapor is added to the air. But is there a limit to how much water vapor the air can hold? To find out, let's zoom in again on the water's surface. When we zoom in, we see that initially, the air can hold more water vapor, leading to net evaporation. But after a while, the air reaches its maximum capacity, and now some water molecules are condensing back into the liquid. When evaporation equals condensation, the air is said to be saturated, and the pressure gauge shows a further increase. The vapor pressure in this saturated air is called the saturation vapor pressure. Now, is there a way to increase the water vapor content in the air even after it reaches saturation? Yes, there is. By increasing the temperature, evaporation exceeds condensation again, and the air's capacity to hold water vapor also increases with temperature. This capacity is known as the saturation mixing ratio. I've explained the mixing ratio in detail in another tutorial on humidity, so feel free to check that out too. The graph on the left and the table on the right show how the saturation mixing ratio changes with temperature. For example, at 20 degrees Celsius, the saturation mixing ratio is 14 grams per kilogram. This means that at 20 degrees Celsius, each kilogram of air can hold 14 grams of water vapor before becoming saturated. We'll dive deeper into this in another tutorial. But for now, that wraps up our discussion on vapor pressure. I hope you found this tutorial helpful. If you did, please consider liking, sharing, and subscribing to the channel. Thank you for watching, and I'll see you next time.